Switch here, so it should be on now.
Okay, so 1 second.
Anyway, I'm sure we're great.
Let's get back in our seats.
Okay, is this good in here? Or,
I think
I mean, it's kind of complicated, but maybe here is better.
that's probably a little better. All right. All right, let's get ready for the next session. You ready if I introduce you?
Sure.
All right, so we're glad to start another lecture series. We're very happy to have Isabel Garcia from the Institute of Advanced Study at NYU and the University of Washington. And she will be telling us about particle physics, gravity, and symmetries. Isabel.
Okay. Yeah, thank you so much for the introduction and for inviting me to give these lectures. It's the first time I'm at TASI. I never got to be here as a student, so this is also like great for me. So yeah, the title of my talks, of my lectures, is Particle Physics, Gravity, and Symmetries, which could mean anything and everything. So what I'm going to focus on in these 4 lectures is, in particular, how symmetry, both the absence of symmetry and the exact symmetries of the standard model, shapes the puzzles, the puzzles of the standard model, and how we go about resolving those puzzles, and how that also, allows us to, and how that sort of like guides both phenomenology and the way that we, experimentally try to probe those ideas. So that's going to be the. And crucially, their solutions of the standard model. So obviously, we cannot do this in full generality. So we have to kind of, yes. Bigger? OK. I can write bigger. Is that big enough? OK. So a rough plan, as a rough plan, we're going to start discussing the so-called strong CP problem. I know Masha has already introduced somewhat what the strong CP problem is in the standard model. This is a particularly good example of how I think, in particular, developments in the way we understand symmetries and symmetry structure, especially in UV completions of the standard model, can give us a new perspective on how to UV complete the standard model in a way to address this particular puzzle. Next, we're going to discuss the topic of and the role of spontaneous symmetry breaking beyond perturbation theory. So in all of the different class of solutions of the strong CP problem that we're going to discuss, symmetry is obviously a very important aspect of it, but also the structural spontaneous symmetry breaking plays a very crucial role, okay? And beyond perturbation theory, that can rise to the existence of what we call solitons or defects. And we'll discuss in particular the role of defects like domain walls and cosmic strings. This is more general, of course, than anything related to the strong CP problem. But we'll sort of keep the thread of a strong CP as kind of the example to kind of have in mind through this discussion. Spontaneous symmetry breaking means that some symmetry, that is a symmetry of the Lagrangian, a symmetry of the axion, is not a symmetry of the vacuum in which we live, but that need not be the case in other phases of the theory. So then we'll go on to discuss how very often symmetries get restored at finite temperature, okay? And in particular, we sort of discuss this in the context of cosmology, and we will see that, again, having the strong CP as our sort of leitmotif throughout these lectures, this has important implications for solutions to the strong CP problem. When symmetries restore at high temperature and defects are produced in the early universe. And then sort of the last topic that follows from here that I want to discuss are the sort of experimental / pheno implications of phase transitions coming from the restoration of a symmetry at high temperature, both in the context of cosmology as well as regarding gravitational wave production. So one of the things we'll do sort of towards the end of the lectures is estimate both the frequency as well as the strength of the gravitational wave signal from, for example, a phase transition that happens at finite temperature at the early universe, or collapse of networks of different defects. So we try to keep it sort of, this is going to be a very pheno set of lectures. We try to put in numbers a lot as we go through. And again, like a lot of the topics we're going to discuss are sort of more general and have relevance beyond, UV completions of the standard model, but we sort of try to keep the strong CP problem as our sort of leitmotif throughout the lectures. Okay, so before I start discussing the strong CP problem, I am going to remind you for the first 5 minutes of the lecture of some very basic aspects of the standard model, especially as far as the discrete symmetries of the standard model are concerned. Hopefully, these are just 5 minutes that are just a reminder for all of you, but can be useful to just, establish notation, make sure we're all on the same page. So, okay, so you all know that the standard model is a gauge theory based on the gauge group SU3 cross SU2 cross U1. This electroweak sector is spontaneously broken by the Higgs vacuum expectation value down to electromagnetism. And the SU3 part is confined in the infrared, okay? So the sort of potential for electromagnetism is a standard, 1/r Coulomb potential. The weak interactions are Higgs or screen, meaning that at distances that are much bigger than the quantum wavelength of the W and C bosons, this potential decays exponentially. So this is the classic screened or Higgs potential. And for the strong interactions, gluons are confined inside what we call flux tubes in the infrared. So we get the usual sort of confining potential where sigma is a tension, the tension of the string or the flux tube. So as you see here, the standard model, the gauge sector of the standard model realizes in the infrared all possible phases that a gauge theory can realize. So there is obviously an incredibly rich structure in the standard model that I'm not going to talk about here. And the dynamics behind spontaneous symmetry breaking, how exactly confinement takes place in the standard model, all of these are, topics in which there is still a lot to learn from, and that are topics of active research, and some of you may even be working on some of these problems. So let me just remind you briefly of the matter content of the standard model, which is going to be the main. The main thing for this first lecture. So as far as the quarks are concerned, we have 3 sets of quarks transforming in the fundamental. One of them is also an SU2 doublet, and then all of them carry hypercharge with various charges. Same thing for leptons, which are now SU3 singlets. And then of course, there is the Higgs, which is an SU2 doublet with hypercharge I have in our conventions. And of course, as you know, there are three families of fermions. So all of this is times 3. So as you know, when the Higgs bed gets a vacuum expectation value, that breaks the electroweak sector down to electromagnetism. So from this table, the fact that the field content of the standard model, the left-handed and right-handed matter content doesn't carry the same gauge charges, in particular under the SU2 group, that already itself tells us that parity is a broken symmetry in the standard model. Okay, parity sometimes we say is maximally violated by the weak interactions, meaning it is as broken as it could possibly be. The same is true for charge conjugation for the same reason, but at this level, at the level of the gauge interactions, there's a question as to whether CP could be a good symmetry of the standard model. And to discuss that, we have to discuss how the Fermion masses are generated in the standard model. So Fermion masses are also due to the Higgs. And this comes down to yes, UJ. Let me write this. Okay, so these are two 3x3 matrices. IJ refers to generation indices. Once the Higgs, so after a spontaneous symmetry breaking, the Higgs gets a vacuum expectation value, and all of these things are just masses for the up quark as well as the down quark fermions. And obviously the same type of interactions are also true for leptons. So in general, these guys are just two 3x3 matrices. You can check for yourself, and you probably have all done it at some point, that if these matrices were real, the standard model, and in particular the mass terms of the fermions, would respect CP. So CP could be a good symmetry of the standard model if these matrices were real. But we know that they aren't, okay? And we know that because, so at this level, these matrices have off-diagonal elements. We find, so the mass eigenstates, the propagating eigenstates of these fermions are the fields where these matrices are diagonal. Okay, so in order to diagonalize a completely general, in principle, complex 3x3 matrix, we're going to need to use two unitary matrices acting on either side. Okay, so we can do that by rotating our fields. Let me check. Rotating our fields in the up and down sector differently. And in order to do that, for each of those two matrices, we're going to have to introduce 4 in total unitary matrices. Okay, so we can do these SU3 field redefinitions on these guys, and these guys separately, and bring these matrices to the diagonal form. This is an important consequence, which is after spontaneous symmetry breaking, but before we do this field redefinition, there are interactions between the W, so the charge W gauge bosons and the quarks that are of this form, okay? These are what are called charge currents in the standard model. So the standard model has flavor changing charge currents at 3 level. So once we rotate to the quark mass eigenbasis, doing this sort of this field redefinition, these indices that here are sort of like generation diagonal now become now sort of get modified by this 3x3 matrix in flavor space, okay? And this matrix, so this matrix that sort of measures the flavor changing interactions between quarks mediated by the W is what we call the CKM matrix, okay? Cabibo, Kobayashi, Moscaba. So you can convince yourself that even though, and this is a unitary matrix, okay? You can convince yourself that the physical parameters in this matrix are 5 angles that are real and 1 phase. One complex phase, the CKM phase. It's very easy to show to yourself that if this phase was 0, these interactions would preserve CP in the standard model. But we've known for a long time that, in fact, the complex phase in the CKM matrix is order 1. Okay? So CP, it turns out, is also maximally violated by the electroweak sector of the standard model. This tells us, in particular, that whatever the Yukawa couplings are, to start with, they cannot be real. Okay, if they were real, we will be able to diagonalize those matrices using real matrices, and the CKM matrix would not have a phase. So those matrices have to be complex, and there is no reason to think that the imaginary part is small relative to the real part in any particular way. So this is what I wanted to remind you mainly about the standard model. So the electroweak sector of the standard model violates all these 3 discrete symmetries, in particular parity and CP, maximally. Yeah.
I know we're focused on the phase, but usually one hears about 3 angles in the CKM matrix.
No. I'm pretty sure it's 5 angles, 1 phase. Is that right? Maybe it's 3 angles, 1 phase. Maybe I got it wrong. I'll check. I think you're probably right, yeah. I mean, you start with 9 parameters, which are... OK, I need to do the counting, yeah. Sorry. Yeah, so there are many outstanding problems, in the standard model. In particular, the dynamics behind electroweak symmetry breaking. Right now, we have a parameterization of the Higgs potential that tells us how, the electroweak sector is broken down to electromagnetism, but we don't really have a theory for the dynamics behind electroweak symmetry breaking. Similarly, understanding how confinement actually happens in the standard model is a topic of active research. The flavor structure of the standard model. So once we go to these diagonal mass bases, as you know, the fermions have wildly different masses. So there's like wild hierarchies of masses both in the quark sector and in the lepton sector. Most dramatically, neutrinos are so much lighter than anything else that we have in the standard model. So all of this structure, all of this very rich structure, a lot of it we don't actually understand. So I could give an entire sort of lecture course just discussing the various puzzles. There's no time for that. So we're going to focus, as I said earlier, on the strong CP problem. So strong CP, as the name indicates, and probably Masha already discussed it, has to do with CP violation, or rather the lack of it, in the strong sector of the standard model. Okay, so the SU3 part. So in general, so in any sort of like general Yang-Mills theory, let's ignore matter first. So let's say there's no charged matter. So we will write the action as containing, the kinetic term, and in 4 dimensions there's another marginal operator we can write, which is the coefficient of the the trace of the GG dual operator, where in my conventions G dual is just okay, and this coefficient, this sort of parameterization here is just a convention, and theta is just a dimensionless parameter at this stage, and as you've probably seen, the trace of GG dual, so GG is symmetric, obviously, under both parity and CP. This term is odd under both P and CP. Okay, so this theta term is a parity and CP violating term that one can write down in a four-dimensional geometry theory. Some comments. First of all, and again, Masha may have already mentioned this, I'm actually not sure. Operator GG dual can be written as a total derivative of a current that is the Chern-Simons current. Okay, so I'll just write it for completeness. Okay. So this means in particular that this theta term, it has no effect at the level of perturbation theory. Okay, the effects of this theta term are purely non-perturbative. Okay, and this is due to the existence of instantons. And these are topologically non-trivial field configurations that in particular have this property, where this surface integral, if you wish, is sort of quantized in the integers. Okay, so normally we're used to, whenever we find some total derivative interaction, we're sort of like integrating by parts and throwing that away. But the fact that there exist in Yang-Mills theory field configurations where the value of that current in the boundary doesn't vanish means that we cannot actually do that, okay? So, okay, this is probably something you already heard. Comment number 2 is that, although it's not obvious from the way I've written it up there, theta is an angle, okay? So if I change theta to theta times theta plus 2 pi, the action will change. Well, not the action, but the action changes by a multiple of 2 pi. And so when we're doing sort of our sum in the path integral over all field configurations, the change of this object is just e to the I 2 pi n, which is 1. Okay, so theta is equivalent to for all n in C. And then finally, if we thought of that theta parameter as a spurion transforming under P and CP, theta would transform as minus theta. And so the fixed points under this operation, if we take into account that, again, theta is an angle, so minus theta is therefore equivalent to theta plus 2 pi n, are actually values of theta that are an integer multiple of pi. Okay, so this means that if theta was either 0 or pi, then there would be no P or CP violation. However, if theta is different from 0 or pi, then the theory violates both P and CP. Okay, so that's all I wanted to say about a theta term in pure Young-Mills. Beyond just the pure gauge theory, well, the meaning of this theta parameter depends crucially on the spectrum of charged matter. Okay, so let me discuss that first in a simple example where we have a single quark, Dirac fermion, that is charged under the fundamental of SU3. So in my notation, these are both left-handed Val fermions. And in general, this mass term will be some complex parameter with some phase that I'm going to parameterize like this, okay? And again, if alpha was neither 0 nor pi, then this thing will be complex and will violate both parity and CP. So naively, we can get rid of this phase by performing a chiral rotation in our quarks. Okay, so we can rotate our two left-handed Val fermions. Let me actually write it as, you may be more familiar if I write it like this. So a chiral rotation takes the left-handed and the right-handed component sort of with opposites. So if I do this sort of field redefinition, I can get rid of the phase of in the quark mass matrix. However, you probably have heard this many times already in these lectures, that the U1 axial symmetry is anomalous. Okay, and in particular, there is also a SU3 square closed U1A anomaly. So this means that, so I need a new Blackboard. Yeah, so this means in particular that under a chiral rotation, the full action of the theory also changes by an amount that is like this, okay? Where this factor here is sort of like the anomaly coefficient of our field content. Dual. So this means in particular that the physical parameters that actually measures P and CP violation is not theta by itself or alpha by itself, but it's actually theta plus the argument of that mass. Okay, so this is the parameter that remains invariant under unphysical field redefinitions of all my fields. In the standard model, we have a bunch of fermions that are charged under the SU3 sector. Their mass matrix is somewhere over there, and you can convince yourself that in the standard model, the physical measurement of both P and CP violation is theta, and now the argument, not of the mass, because now this is a matrix, but the argument of the determinant of the quark mass matrix, which we can write, including all the quarks, as the product of the two Yukawa couplings in the up and in the down sector, okay? Now, remember, we sort of argued that these two matrices cannot be real matrices, okay? We know these guys are complex. There's no reason to expect that the imaginary part is small. So we expect, in particular, the argument of the determinant of this matrix to be an order 1 number. Okay, so our expectation is that in the standard model, this thing will be order 1. So in particular, there is no reason why taking theta bar to 0 in the standard model is not a technically natural limit in the sense of a tooth, right? If we take theta bar to 0, in the standard model doesn't become parity symmetric or CP symmetric because parity and CP are already badly broken by the electroweak interactions. Okay, so this is what we expect, but as I'm sure Masha has already mentioned, this is not what we find in nature. Okay, experimentally. The most sensitive probe or of CP violation in the standard model is the electric dipole moment of the neutron. Okay, so the prediction in the standard model up to some order 1 numbers in front is proportional to theta bar. It's something like 10 to the minus 16 theta bar, and then this is typically measuring units of the electron charge times centimeter. So this is a theoretical prediction. If one computes what this dipole moment is in the presence of this theta bar term, experimentally, no one has ever observed an electric dipole moment for the neutron. Okay, neutrons have a magnetic dipole moment, but experimentally, all we have is an upper bound currently on this vector, which is smaller than 10 to the minus 26 e times centimeter, okay? Which means that, in fact, in the standard model, theta bar has to be smaller than at least 10 to the minus 10. Okay, so that's 10 of magnitude smaller than our naive sort of experimental expectation based on the underlying symmetries, the underlying symmetry structure of the standard model. Okay, yes? Sorry, can you speak a bit louder?
The standard model will have a discrete gauge symmetry, and then that means that you should have a choice of a discrete theta term.
Are you talking about the mod C6? Yeah, so technically the global structure of the standard model is SU3 cross SU2 cross U1 mod C6.
So then that means there could be a discrete theta term. Does this at all affect the story?
What do you mean a discrete theta term? That theta could take discrete values, or?
Yeah, you can have a theta term associated to the gauged discrete symmetry. So why is it 0? So that also has to be big.
The issue is why is it 0 and y?
So I'm a bit confused about how to think about that C6 factor as. So okay, so I think of this factor as coming from the absence of matter, right? Like there are various global symmetries that the standard model will have, which are the center symmetries of SU3, U2, and U1. And then in the presence of matter, it turns out like the C6 factor is left over.
Yes. So,
but I'm supposed to think of that as like a gauge symmetry of the standard model. But it's not like a new gauge symmetry. Like I don't think like it will change anything about. Well, it will definitely not change anything about the theta term of the QCD sector. I'm not sure how I would think about it in terms of a theta term for this discrete factor itself.
Okay, maybe I can ask you later. In the annual theory, when you mod by the sector,
Yeah.
you have theta, but then you also have the discrete theta term.
Okay.
Would couple the one form gauge field.
Okay.
And then both theta and discrete theta term also could shift.
I see. And these are like this would be like independent parameters somehow.
Yeah. So there is another triple parameter which I'm asking whether which also plays theta.
Okay.
Is this theta that theta, or
I mean, theta bar is like the only thing that's physical here. Yeah. Yeah, maybe we can discuss more later. Yeah, so basically, in one sentence, the strong CP problem is that it is not possible to understand why theta bar is so tiny not just smaller than 1, but like smaller than 10 to the minus 10, based only on the symmetries of the standard model, okay? So solving a strong CP requires either new dynamics or / new symmetries beyond what we have in the standard model. So there are roughly 2 classes of solutions. To this problem. One, we can vaguely sort of think of it as a relaxation mechanism, which could be the QCD axion, and then there is a second set of solutions that we can think of them sort of as symmetry-based solutions where that are based on restoring P or CP, really, and or CP in the standard model. So, and in principle, restoring parity and or CP could provide a solution to the strong CP problem. We're going to discuss this more later in the lecture. And one thing I wanted to mention that maybe I'll get back to sort of towards the end of the lecture if there's time. You may have also heard about something called the massless up quark solution to the strong CP problem. So this is just a statement that, and we can see it here already in sort of our toy model, which is that somewhere here. So if this guy if the mass was 0, so it would take mod m to 0, this phase is which means that this basically allows us to rotate away completely whatever theta dependence we have, and then we can set theta bar to 0. So maybe I'll mention something more. So that solution doesn't work because for a number of years now we've known that the quark mass, the up quark mass, is actually non-zero. But for a long time, it was sort of a mysterious solution in the sense that there's no symmetry that is restored when you take the mass of a fermion to 0, right? Because the symmetry you would restore, which is the U1 chiral symmetry, is anomalous. Maybe these days, with the developments in generalized symmetries, we will have another interpretation of what the massless quark solution is. I am not sure, but if I have time, sort of at the end, I'll sort of maybe come back to that and say a few things. So mostly, I want to focus on this lecture and also probably half of the next lecture on discussing symmetry solutions that you're probably less familiar with. But I'm going to say a couple of things about the axiom first. So I'm not going to say a lot because I know Masha has discussed a lot of things about the axiom, and in particular in the context of how it can be dark matter. There are many nice things to say, but there are some things that I'm sure she also hasn't said, so we're going to sort of briefly discuss this. So the idea of the QCD axiom is that it's sort of to introduce a new global symmetry that is anomalous, okay? And in particular, it has a U1PQ S3 square anomaly. So the idea is that the only term that breaks this PQ symmetry is a term like this. So this coefficient is just, well, let me just first write it all. A over F trace GG dual. So this is the axion, which is a Goldstone boson of this spontaneously broken U1 Petequian symmetry. F here is the scale of a spontaneous symmetry breaking of that U1PQ. So under the U1PQ symmetry, the axion sort of just transforms. So this acts as a shift symmetry in the axion, okay? And this coefficient here is a model-dependent coefficient that depends on whatever way we choose to write down the UV completion of the axion model. Okay, it corresponds to the anomaly coefficient of whatever fermions in the UV completion carry this Petequian charge, and it will be an integer. Okay, but for now this is not super important. So the basic idea is that we introduce this anomalous symmetry, and then non-perturbatively, QCD generates a potential for the axion V of A such that the axion gets a vacuum expectation value, and the vacuum expectation value is precisely such that the effective theta bar that we see in our universe vanishes. Okay. So I should have said that if we add a term like this, in total, right, the coefficient of that GG dual term will be no longer theta, but it will be, sorry. This will be the coefficient of that GG dual term in the presence of a theta term. The axion, really theta bar, sorry. So this is what I'm going to call sort of the effective theta bar in the presence of the axion. And then the potential for QCD that you can compute using, for example, Carroll-Lagrangian techniques. You can show that actually this, the minimum of that potential is precisely when this combination is 0. Okay, so that's beautiful, and looks a bit like a very minimal solution to the strong CP problem, and for that reason, it's also the most popular solution to strong CP, and a huge amount of experimental effort goes into trying to discover the QCD axion. Now, so the symmetry that we've introduced to solve the CP problem in this axion construction is not a real symmetry because we need to start from the get-go with something that is an anomalous global symmetry. Okay. Therefore, it is broken. So in this sort of in this vanilla sort of implementation of it, we assume that it's only broken by QCD, but the fact that it is not a good symmetry at the quantum level also begs the question of, how robust is this mechanism? And by robust, I mean, against breaking of this U1PQ symmetry other than QCD. And we should especially ask this question, given that, as I'm sure everyone here knows, we've known for a long time that gravity is expected to violate all global symmetries. The U1PQ symmetry cannot be gauged because it's anomalous, therefore it has to be global, and therefore therefore it has to be broken by gravity in particular, but there could be further sources of PQ violation. And so this just begs the question of how broken by only a tiny bit broken by QCD this symmetry has to be for this mechanism to work. So we can try to get a sort of quantitative idea of that, how robust or not robust this mechanism is by considering, say, a higher dimensional operator that breaks the PQ symmetry. And I'm going to parameterize that as, so there is some dimensionless coefficient, little lambda, and I'm going to consider, say, an operator that is of, a certain, this is a higher dimensional operator and violates, say, the PQ symmetry by n units. So this complex field, the phase of which, again, is the axion. And this would be suppressed by some scale that I'm going to call capital lambda. Well, in 4D, we can write it like this, okay? And in general, this parameter, again, doesn't have to be real. In general, it will have sort of a general phase delta. So after spontaneous symmetry breaking, so you can think of the complex field in the far infrared as just it's set to its BEV, and then the phase again is the axion. So you can show that a term like this, so a symmetry breaking term like this, would generate a potential for the axion, an additional contribution to the potential for the axion that I can write in this way. Okay, where this delta m squared would be sort of, so it's the coefficient of the quadratic part of the axion, so it's the additional contribution to the axion mass from this, from some symmetry breaking contribution like this, and we can write it in terms of our various parameters in this way. We'll put in numbers in a second. -2. Okay. So this means that in general, the full potential for the axion will contain the contribution from QCD, the contribution from the non-perturbative QCD instantons, as well as an additional contribution from any other physics that breaks the PQ symmetry. And as we're going to see now, what this means is that this additional contribution to the potential will sort of destabilize the minimum of the overall axion potential in a way that the overall, this effective theta term is no longer zero in general, okay? So this mechanism will remain successful or not, depending on how not zero this is, okay? It has to be as small as, as much below sort of 10 to the -10. And we're going to see now what it takes for that to be the case in general. So, okay.
What about the theta bar? Like, we know it's not zero, or it might be zero.
It might be 0,
Okay.
yeah. I mean, once, so I'm not actually, I don't actually remember exactly the numbers, but I think, so we know theta, so I said earlier that, theta equals pi was also, preserves parity on CP. We know that theta is not pi, and I think the reason we know mostly is because that would affect properties of nuclear matter in a way that would be incompatible with what we know about nuclear physics. But basically, once theta is below 10 to the -3 or so, there's no difference to anything else. So theta is 0. Yeah, we have no bias for. But I mean, yeah, some parameter being 0, obviously, it makes you feel like there needs to be a very special reason behind why that is the case. So But yeah, we certainly don't have any kind of lower bound, not strictly speaking. Yeah, so we have in general some potential for the axion. It is more convenient to write it as a potential for this effective value of theta bar. So if we think of it as a potential for theta bar, as we said earlier, the QCD contribution always has a minimum at sort of theta bar equals 0. And then this additional contribution we just calculated looks something like this. So 1 minus cosine minus theta bar plus delta. Okay. So you can see already, and I'm actually just setting n equals to 1, just to not to complicate the expression more. But so you can already see here that if the phase of this new operator that breaks the PQ symmetry, if this phase is not perfectly aligned with the value of theta bar that we have in the standard model, the minimum of this part of the potential is no longer going to be at 0. Okay, so you already kind of see where this is getting at. So if we ask, where is the minimum of this potential relative to theta bar? There's the QCD part, and then we're going to have sine. Okay, something like this. For a small theta bar, so that we can self-consistently, so this thing is, we know is itself minimized near theta bar effective equals 0. So we can actually expand this as second derivative theta bar effective, which in other words is also just the mass of the axion, the QCD, the mass of the axion sort of that we get from QCD that I think Masha calculated again using Lagrangian linear in theta bar. And you can also expand this for sort of near theta bar tiny. And this would be theta effective cosine delta minus theta bar plus. Okay, the bottom line is that. Yeah, okay. So in this theory, the sort of the vacuum expectation value of this theta bar parameter can be written in this way. Delta R here is the ratio of the contribution to the axiom mass in this new dynamics relative to the original axiom mass from QCD. Okay? And we've just said that just on experimental grounds, the overall size of this thing has to be smaller than, in sort of, the overall size of this thing needs to be smaller than 10 to the minus 10, okay? Any questions? Okay. So this needs to be smaller than 10 to the minus 10. This means that either for some reason, any CP violating phase in any UV completion is perfectly aligned with the CP violating phase of the standard model, or if that's not the case, so if delta is under the one phase, which is what would be our natural expectation, then this ratio of mass scales than 10 to the minus 10, okay? So already this means that any other contribution to the axion potential other than QCD has to be subdominant relative to QCD dynamics by at least 10 orders of magnitude, okay? So that gives you an idea of the extent to which QCD has to be the main sort of ingredient in this solution.
Could you say, kind of like we were assuming QCD gives you 0 theta effective, couldn't it be that they cancel out? And
well, this is something that we can compute just using the low energy sort of behavior of QCD. It's complicated because QCD is non-perturbative at low energies, but the Kerr Lagrangian allows us to do this calculation. So this potential, yeah, and I mean, this has done now to various degrees of sophistications. And this potential is a potential that is sort of like periodic. It's not quite a cosine potential, but it's known to have a minimum of theta variable 0. So that's not something we can play around with. Okay, so more, more dramatically, if let me sort of write it in this. Can you guys see here? Okay, so let me put in numbers. If we say that, so this scale, capital lambda, in principle, could be any scale. Obviously, we can take it in principle all the way up to the Planck scale. That would be sort of the best in the sense of like the most suppressed effect. So let's say, we put lambda all the way to the Planck scale. We take the scale of PQ spontaneous symmetry breaking to be, say, of order 10 to the 12 GB, which I believe is still consistent with current constraints. And this will correspond to a QCD axion mass of order 10 to the minus 5 electron volts. So if I put in these numbers, and we express this delta m squared in terms of the various fundamental parameters like lambda, etc., what we find is a constraint on the size of this dimensionless coefficient. And for these numbers, what we find is that the size, that overall parameter, needs to be smaller than 10 to the minus 55. Okay. So in other words, if there is any other PQ breaking that is not QCD, that better be so tiny. Okay. And notice, I'm being generous here because I've taken lambda to be as the Planck scale, which is the highest it could possibly be. If I bring lambda down, which it could be, this could be some, CP violating operator coming from some theory that does baryogenesis or a solution to the hierarchy problem. It could be all sorts of things. Lambda doesn't have to be in Planck, okay? But taking lambda smaller than in Planck would only make this worse. So this is just sort of to give you an idea of, how close to an exact symmetry this PQ symmetry has to be, even though it's an anomalous symmetry. You can also relax. So here I've done everything for the case where n is equal to 1. So I've been considering the case where the leading operator that breaks the PQ symmetry is a dimension 5 operator. You could not do that and say, well, if I assume that this coefficient is order 1 and the phase is order 1, then what you find is a constraint on the sort of the dimension of the operator that breaks the PQ symmetry. And it turns out that the overall dimension of the operator, so in this case, sort of the combination of 2n plus n. Yes. Let me write it like this. So the dimension of, the dimension of the PQ symmetry breaking operator would have to be larger than 13 or so, okay? So for some obscure reason, even though this is a global symmetry, operators of dimension 5, 6, 7, 8, all the way up to 13 have to be absent. And suddenly, the leading operator that breaks the symmetry is 13. So you see that, this is sort of like a somewhat, definitely not robust against breaking of the PQ symmetry other than QCD. And this is what goes by the name of the Axion quality problem. Okay, which is just a statement that basically any other dynamics that break the PQ symmetry of the axion basically destabilizes the strong CP problem solution. Okay, any questions about that? I feel like that board got a bit crowded.
So you've got about 15 minutes.
Sure. Yeah, so basically, I mean, what this tells us is that in any compiling solution to the strong CP problem that is based on the Axion mechanism, this U1PQ symmetry must arise as an accidental symmetry, presumably coming from some, some additional structure in the UV. So this is not to say, so, I sort of painted a very bleak picture for the QCD axion. There is an axion quality problem. This is not to say that the axion quality problem cannot be addressed, okay? If you have some UV completion where the symmetry appears as, very approximate for some reason, then, there is a perfectly fine solution. So things people have tried include, gauging a CN subgroup of the U1PQ symmetry. So U1PQ itself has to be global, but there's no particular reason why some discrete subgroup could not be gauged, and that would forbid certain operators of dimension lower than n from appearing in the Lagrangian. Sometimes also models where the axion sort of appears as a composite degree of freedom. So this basically requires the presence of additional SU engaged groups, and in that case, sort of, the axion is sort of realized as a composite object in these UV completions, and in those cases, the U1PQ symmetry can also be protected if this n is large enough. So this is a little bit in the spirit of, baryon number in the standard model, where sort of the gauge structure and the gauge chargers of the various fields sort of don't allow us to write the sort of, the lead in order kind of baryon number violating operator. So it's sort of like in that spirit. And then perhaps to me more interesting is that the axion shift symmetry itself could be protected. So further corrections could be protected by gauge invariance in a sort of higher dimensional theory. So for example, the simplest thing would be a 5-dimensional UV completion on a circle where our axion is sort of comes from, sort of the Wilson line phase of the higher dimensional 5-dimensional gauge field. So for some U1 5D U1 gauge field. So in that case you could think of the axion as the A5 component of that vector. Okay, and more generally, in higher dimensional theories with different numbers of cycles of different dimensionalities, typically the integral, sort of the closed integral over some n-dimensional cycle of some higher dimensional n form produces also a pseudoscalar particle that in principle could be the axion. Okay, the QCD axion, or perhaps many other axions could be realized in this type of higher dimensional context. Yeah, and so this is a particularly sort of natural resolution of the strong CP problem coming from the structure of theories like a string theory. I'll just give you a reference to read about this called the string Axiverse et al., which sort of discusses this more in detail if you're interested. This is theory. So yeah, so this is not to say that the axion quality problem cannot be solved. It can be addressed, but then the phenomenology of all of these different implementations can actually be quite different from the vanilla sort of QCD axion mechanism. Okay, and then the phenomenology and experimental implications need to be studied sort of like in this extended context. So yeah, and this is an area of sort of like active research. Lots of things to do and sort of understand about the implications of all of these ideas. Okay, Any questions about axions? Okay, so what I'm going to introduce for the last 10 minutes of today, and we'll continue also tomorrow, are solutions to the strong CP based on symmetry, okay? So we said earlier on that, again, since having theta bar to be non-zero breaks both parity and CP, if there was some way in which either of those symmetries could be restored, they could be made like good symmetries of the standard model, then that would allow us to set theta bar to 0. Of course, neither P nor CP are actually good symmetries in our vacuum, which means that those symmetries would have to be spontaneously broken, okay? And so in that case, whether these symmetry solutions implementations are good or not comes down to how small can we make theta bar in a theory with restored parity or CP while complying with all other experimental constraints that we have. So there are basically two classes of these solutions. I'm going to mostly focus on the parity solutions, but let me mention. Actually, the first solutions proposed in this way were actually solutions based on restoring CP, not parity, and these were proposed by Ann Nelson and also by around 1984. So in these models, all CP breaking has to come spontaneous. So all breaking has to come from a spontaneous symmetry breaking. However, having the phase in the CKA matrix to be order 1, but theta bar so tiny is tough, okay? Meaning that it typically requires additional structure in these models. These models are typically fine-tuned as far as the scalar potential is concerned. They also typically require introducing additional discrete global symmetries that very often have to be exact. So it just makes the whole thing a little bit of an overkill exercise, and it's not clear that the problem, you're actually solving any problem. You're introducing a bunch of extra structure that also seems very ad hoc. So I will not be discussing those solutions, even though I want to emphasize, this was the first time these ideas were entertained. I'll be discussing mostly solutions based on restoring parity, and these were mostly developed by Claudia Babu and Ravi Mohapatra, I think in the 89, as well as Barr et al. Around a little bit later. So the main observation here is that so P in the standard model, P breaking in the standard model is due to the electroweak sector. So the idea is just to extend the electroweak sector and restore CP. Okay, so that's kind of like the basic, very simple idea behind these solutions. So I'm going to introduce kind of the basic of how that idea works, but I also want to emphasize that unlike the QCD axion, this type of solutions that are based on restoring symmetries that then have to be spontaneously broken, they have a different. So they are motivated, I would say, by different considerations than the strong CP problem. Okay, people like Michael Dine for a long time, or even people today like Dan Harlow. If you ask them, they would tell you that there's no reason why symmetries, space-time symmetries like parity or CP, cannot be gauge symmetries in a UV completion. Okay, so that is a possibility. So if that was the case. So if that was the case, the symmetries can actually not be broken explicitly, okay? They can only be broken spontaneously. And then it would be so it would be the job of whatever, spontaneous symmetry breaking mechanism to explain, all of the parity breaking and CP breaking structure that we see in our world, okay? So I feel like, this type of solutions are also motivated by, considerations that are very different from the QCD action, which is a very sort of like bottom-up motivated construction. Yeah, so you want to read more about this. For example, Michael Dine has written about this, I think, extensively. So I have here. I'll just give you a reference. 11, and then also in the context of CP itself, a paper by Choi, Kaplan, and Nelson discussing whether this could also be true for 1983, 93. Whether this could also be true for CP, okay? And I think more generally also, if you just look at the standard model that has the CKM phase that is order 1, where parity is completely broken, that also begs the question of like, where is this coming from? So from that perspective, just regardless of a strong CP problem or not, ideally you would have, all of these features of the standard model. You would like to be able to understand this from some kind of, some underlying dynamical structure where all these, parity breaking, CP breaking are actually the result of some kind of underlying dynamics as opposed to something that we put in by hand, okay? And in that context, then, addressing other issues like the strong CP problem can come as an accident if you want, which will be, in my opinion, like a very natural sort of resolution of this puzzle. Okay, so in the last 3 minutes, I'm going to just write down kind of the basic structure of these models that solve strong CP from parity, and then tomorrow we'll just take it from there to discuss further. Yeah, so basically, the most minimal kind of implementation of something like a spontaneously broken parity that is consistent with the standard model is it requires extending the gauge group to include an additional SU2 factor that I'm going to call SU2 right. And it also requires expanding somewhat the matter content beyond what we have in the standard model. So I'm going to write it only for the quarks. Obviously, for the leptons is the usual story. So the standard model is sort of the same as earlier, except all of the guys are obviously singlets under this SU3. Sorry, under this SU2R. And then U1 is the same as the usual hypercharge assignments. And then, so the matter content in these models has to be sort of extended to include what you can think of as an extra copy. So every time I write a dagger, hopefully this you obviously know, every time there's a dagger, this means this is a 2-component right-handed Weil fermion. And then guys have charge assignments. So these are also QCD fundamentals. They are all singlets under SU2 left. And then they carry the same SU to right charges that the standard model carries under SU to left, okay? And then
Big D prime over dagger there.
no, so I've written it exactly so that you see that like the left-handed partner of this right-handed guy has the same SU2, has the same, SU3 charge in particular. Yeah, so every time there's a dagger, you can think of this as having like an alpha dot index, but every time there's not a dagger, it's just a left-handed guy. Yeah, and the U1 charges are the same. Okay, so in this theory, it turns out that it is possible to restore parity. But mind you, any of the discrete symmetries of the standard model, or actually of any theory, are sort of to some extent like up to us to define, okay? And the way we define whether there is a symmetry or not will depend also on the field content. So in particular, this is the last thing I'm going to write today. So in this theory, with this field content, it is possible to define a version of parity that, sometimes is sort of goes by generalized parity that corresponds to, if you want, ordinary parity plus, let me write it like this, exchange of the standard model fields as well as the new fields that I've introduced that I'm going to call loosely sort of like these mirror fields. Okay, so basically this would mean the FU2 gate sector guys get exchanged with the SU2 ray guys. Similarly for the matter content, these guys, which are left-handed fermions, get exchanged with their sort of right-handed counterparts. By now, these are the right-handed counterparts, not in the standard model, but in this kind of mirror sector, so with the primes. And similarly, H gets exchanged with its its extra Higgs. However, crucially, because the SU3 and U1 factors are not sort of duplicated in these constructions, these guys transform as usual under P, under parity. Okay. So and in a theory like this, with this field content, this is as good a definition of parity as your ordinary parity, except that this has a chance of being an actual discrete symmetry in this model. So I'm going to stop here for today, and then tomorrow we'll see how, in fact, this symmetry basically forbids you from having a theta term at tree level. Okay, and then it's only through the spontaneous breaking of this symmetry that something like a theta term can appear. And then so we'll take it from there and discuss a little bit more the structure of these models.
One question, maybe?
That was me, right?
Yes, that was you.
So sometimes people explain fine-tuning problems with some kind of anthropic principle.
Some kind of anthropic principle? Okay.
Is there anything like that can be said here?
That is a great question. So I would say that, unlike, for example, the hierarchy problem or like the CCE, where, you can at least try to make those arguments, there really isn't anything like that that you can do for a strong CP. And this comes back to this question that was asked earlier, which is, if theta bar was maybe like, if our bound on the neutron EDM were such that theta bar had to be like smaller than 10 to the minus 3 or something like that, then you could make some kind of anthropic argument because, theta bar bigger than sort of like something like that, 10 to the minus 3, 10 to the minus 2, would change the properties of nuclear matter in a way that I think it would be incompatible with like certain bound nuclei existing or things like that. So you could make that argument if the bound on theta bar was a little bit weaker, but nothing changes once theta bar is below that level. So there's really no argument along those lines that you can make as to why theta bar would have to be like 10 to the minus 10. Yeah, so that doesn't really work, unfortunately. I would say that really suggests that as far as this theta term and CP violation is concerned, like that really calls for a dynamical mechanism.
All right, well, let's thank Isabel again. And we will scatter back here at 2 p.m. after lunch.
Thanks.
Is there, maybe you'll talk about this, but this sort of looks like neutral naturalness, but isn't. Like, there's only one SU3 and not 2.
Yeah, there's actually, it's funny because, even without thinking about naturalness, this is the simplest thing you can write that would restore parity, but I'll mention this tomorrow, but like the Higgs sector of these models do have like the structure of neutral naturalness models. So that kind of also, help, oops, I have this still here. Yeah, so that helps a lot with like, the absence of fine tuning in the data sector.